Display. Picture generation.
Welcome to the Cube. Please identify yourself.
This is a lecture about the future, about your future, about Britain's future, and indeed about the future of mankind. Let's begin. Yes, this is a lecture about the future. When the historians of the future look back on our time, they'll say that in the final years of the 20th century, the mechanical age gave way to the electronic age. That is certain. But Britain's future, its share in what's going to happen, is more of a problem. And your future, your share in what's going to happen, is very much in your own hands. Though I hope that what you're going to see and hear today will help you to determine that future, and perhaps Britain's too. For the truth is that those who will prosper in the future are those who best understand the technology of the electronic age and who make the most of it. And that's true for individuals, for companies, and for nations. The opportunity in your lifetime is what we're on about today. Mankind will grow richer in proportion to the speed with which it adopts information technology. But what is information technology and what can it do? Most of you, I suspect, already know. Many who do not understand what it can do look upon the new technology as a threat. But in truth, it will be of the greatest benefit to mankind, properly used, and you must use it.
Man is not the strongest, nor the swiftest creature on this planet. But he has the best brain. He can convert what he perceives from a sight to an insight. His ingenuity more than compensates for all his frailties. He can and does devise means of overcoming them. He invents an appropriate tool a machine.
The computer is such a tool, such a machine. Like all tools, it helps man to do what unaided he can't do, or can't be bothered to do, or can't do in the time. And yet it's like no other tool, both in what it can do and in how it does it. This is the surface of a computer chip seen through a scanning electron microscope. The chip is the first of man's machines that has no moving mechanical parts. These are moving electrons. The computer helps man to make up not simply for his physical shortcomings, as other tools do, but for his mental shortcomings too. It increases his power to think. It speeds up his calculations and his mental processes. It hastens his commands and takes over in his absence. And it does all this by handling information. It's important to understand what's meant by information. Information is something that somebody needs to know, but it's not the same as knowledge. It's a précis of someone's knowledge made available to someone else. But not all knowledge can be reduced to information. Only that knowledge which can be expressed as information can be handled by a computer. And to do that, the information must be converted into data. Data is the precise formulation of information, and it is that precision which enables it to be processed by a computer. Knowledge is everything we know. Information is that part of what we know that we can pass on to others. Computers hasten that transfer, and in the future, computers will pass on more and more to increase the spread of information in every sense. They'll handle ever-increasing amounts of data with ever greater ease and in ever greater detail. But however much information is provided, man still has to make the choice. Man alone knows how to go about things. We have to make the decisions. The technology makes information more available and thereby enables us to get on with things better informed, better able to make things happen, better able to use our time more profitably. It makes us more powerful. So there's no substance in the argument that the computer is something to be afraid of, something that will elbow man aside. On the contrary, it's something to be proud of. It's the best machine man has yet devised, and it didn't happen overnight.
Charles Babbage is regarded as the father of the computer. He did his early work at Cambridge 170 years ago. He designed a complex mechanical automatic calculating machine, a design far ahead of the manufacturing technology of the time. They say he was born a century too early. The introduction of electricity led to the development of electromechanical calculating machines, which needed punched cards and tape to program and store information. The first real working computer with a stored program was built in Manchester 40 years ago. It contained thousands of thermionic valves and filled a room the size of a small house. At today's prices, it cost almost £1 million. The smallest home computer on the market now, which costs much less than £100, can do more than that first computer. That is the measure of the micro-revolution. The transistor replaced the valve in the next generation of computers. And the microchip has replaced the transistor in today's fourth generation of computers. With each new generation, computers have become cheaper, more powerful, and easier to use. Machines for everybody, not for experts alone. and the fifth generation is upon us.
It's emerging in our laboratories at this moment, as you'll see later. The computer is already the most versatile tool man has yet invented. It can handle figures. It's good with words. It can be informative because it can find out. It can forecast and answer the question, what if? It can take control of a machine or a process. It can plan the progress of a project. It can teach without tiring. It can entertain and compete. But it cannot think for itself. It can only do as it's told. And that's precisely because it is a tool, a machine, a product of man's ingenuity. And it's only a beginning. It's a machine still in its infancy. In information technology, we're still in the era of trial and error, still saying, let's try this and see what happens. And often what happens is unpredicted and unpredictable, but it's man who makes the mistakes. Remember, the computer only does what he tells it to do. If the computer is overloaded, who loaded it? Who made the mistake, man or machine? Answer, man. We're still blundering about in the dark, waiting for another Faraday to shed light on it. He was a man possessed of many talents and skills, not a specialist, a genius, interested in everything. A professional who took concepts and discoveries from many branches of science and created new, practical, working applications. Applications like the dynamo that shape our world today. Perhaps one of you here among us now is a Faraday, who'll peel off the jargon of our endeavours and make everything clear. What's certain is that you, who are on the threshold of your career, have come into the world when the computer is on the threshold of its career. It's the onset of a revolution. Not just a revolution in technology, the creation of a new tool to assist man in his calculations, but a second industrial revolution.
The first industrial revolution was essentially a transformation in the structure of society. A transformation brought about by a change in the character of production. The change consisted in the shifting of a tool from the hand of the craftsman to a mechanism, a machine. The weaver was no longer alone at his hand loom in his attic. He was one among many at a power loom in the mill. Because the machine was harnessed to a new source of power, which necessitated a collective process of production, a factory.
The new mechanism, the new machine, the computer, may yet create no less fundamental a transformation. It will certainly change the way things are done and the nature and the number of jobs to be done. It already has and is. The customer at the cash point, the motorist at the filling station, the train driver at the railway station, the pilot coming into land, the housewife at the microwave, the musician playing the synthesizer, the broker playing the market. They're all taking advantage of information processing and technology. They're citizens of the electronic age, whether they realize it or not. In the shops, the barcode is the signal of the revolution. for it not only facilitates the purchase, it regulates the stock. A barcode doesn't simply indicate that this is a tin of beans. The width of each line contains precise data. It proclaims where it came from, who made it, and what it is. And the information is double-checked. A laser beam at the checkout scans the barcode, decodes the information, cross-refers to the electronic file, and comes up with a price. The customer takes away both the purchases and a detailed statement of every purchase. The supermarket has all the information too. Information about every item goes into the computer, and at the supermarket head office they know exactly how many have been sold throughout the country and where. That means they know how many more to buy, and where and when to dispatch them. They need that information if they're to manage the business effectively. But the information can go further than that. It can be instantly conveyed to the makers of the beans, to the manufacturer of the tin, to the printer of the label. Everyone who needs to know can know. And with EFTPOS, information technology helps the customer to pay for the purchases.
EFTPOS, electronic funds transfer at the point of sale. It is the complete transaction, a simultaneous transfer of goods and payment.
How would you like to pay them? Cash, cheque or EFT?
EFT, please.
Thank you.
The terminal reads the customer's card, while the customer keys in his personal number that only he knows. The value of the transaction is automatically transferred from the customer's bank account to the retailer's bank account. The customer can see at a glance both what he has spent and what remains in his account.
Thank you very much.
The retailer knows both the value of the purchase and what has been purchased. Information immediately transmitted to stock control so that the supply may be replenished and the customer's preference monitored.
That is the very essence of the use of information technology. Everything you need to know all at once. Every stage of the shop's transaction can be done laboriously by hand. The technology makes it faster, cheaper, and much less hassle. It takes away all the boring bits, the irritations, the confusion, and the waste. It also makes the supermarket efficient and profitable, able to stay in business and serve its customers. And the technology already exists to transform shopping beyond all recognition. Some people will choose to do it all from home, making routine purchases and paying for them using their television sets as computer terminals. Others will spend whole days in retail parks, ordering their purchases with a word screen, turning the electronic pages of holographic catalogues, booking a holiday after viewing what's in store for them, having a face print identification to certify their creditworthiness. You could even go shopping in Paris without setting foot out of Putney. Businessmen already do. Using what's called TraderNet, ICL's electronic clearinghouse system, companies can order supplies, organize their dispatch, invoice for payment, and arrange for payment across the country, across the Atlantic, around the world, without posting a letter or sending a salesman. People don't have to travel. Paper doesn't have to travel. Only the information travels. Distance is no obstacle. Two technologies have come together: the ability to process and retrieve information and the ability to transmit and receive it. Computing and telecommunications have converged to produce information systems that span the world. At my desk, I can have all the information I need at my fingertips and share it with anyone I choose on the network. My mail can be handled electronically, inward and outward, keyed in, or handwritten, or spoken. It can even be translated if necessary, although machines often find human language ambiguous. My phone calls can be received, recorded, logged, intercepted, returned. And if I'm interrupted, the machine will remind me where I was up to. Check back if needed. Resume when instructed. I can whistle up anything from the file because this is the file. I can produce the accounts, check the accounts, and most important of all, I can analyze the accounts and ask, what if? What if we raise the price and sell fewer? What if we lower the price and sell more? What will that do to the profits? The computer can model scenarios of the future. We don't have to do it and then find out from bitter experience. The computer calculates the consequences in advance. I can look back and I can look ahead. And I can do all that, not in solitary confinement, but as one link in an international network. And I can even take it all home, but still be in touch with everyone else.
Information technology is not merely a means of shifting vast amounts of humble and routine work in the office, though it does that efficiently. It is the means of getting the right information to the right people at all levels, so that their decisions may be based on the best information available, and not just on a hunch, instinct, or habit. And this information can be up to date, online, and about many things: money, design, project planning, statistics. It can be manipulated, modeled, and experimented with to test various scenarios for a possible future. Furthermore, information technology allows more people to be party to decision-making, so that those down the line are not distanced from the decisions. It is altering the whole management structure of companies. Instead of a pyramid, with those at the top remote and those at the bottom uninformed, everyone who has something to contribute to the success of an organization can make an input. It is no longer a question of A telling B, who tells C, who forgets to tell D, and the message gets lost down the line, but of everybody being in the know. And perhaps the decisions taken will be wiser and more effective.
And this is as true in the factory as it is in the office. You'll have heard of CAD and CAM. The first is computer-aided design, the second, computer-aided manufacture. Both are at work now in industry. The modern designer sits at a computer terminal, not at a drawing board. The design he creates is displayed on the screen.
That went into it. It can recall his first thoughts, his revisions, his amendments, and what other people have done. It can answer the question, what if we tried this, or that? And it can free the designer from 1,000 repetitive chores and enables more complex design solutions to be investigated. It can simulate the design to ensure the design specification has been met. This is a design right first time approach, an approach to ensure that neither time nor money is wasted in producing poor quality products, products which will require extensive modifications. And there is no gap between design and production. The same information is available to both.
Computer-aided manufacture ensures that what was designed is precisely what is made. Manufacture consists, in essence, of fabricating and assembling the right parts in the right order, which means that the right parts have to arrive at the right time, not just from the store, but from the supplier. Computer-aided systems achieve that with precision. Everything where and when it's needed, just in time. Because the information that went into the original design is now in the database, everything can be checked against it and quality assured. There's no question of the computer saying, oh, that's near enough. It's either right first time or it isn't. And if it isn't right, it's rejected and the reason given. The only snag in many factories so far is that all those computers, replacing drawing boards, motivating robots, controlling stocks, sending out invoices, calculating the wages, are locked in their separate tasks, uncommunicating, islands of automation. But no computer should be an island unto itself. There should be, as we say in the trade, computer integrated manufacture, SIM, and there is. It's not a master plan, everybody compelled to do everything in the same way. That would be pointless because it would inhibit innovation. So not a plan, a vocabulary, so that the machines speak the same language and understand each other. With better communication, SIM makes it possible to produce precisely what the customer ordered. It enables the factory to react to the changing demands of the market. We call it flexible manufacturing. Already on the shop floor, a range of machines, each controlled separately by its own microprocessor, can all conform to a set of rules and standards known in the business as Manufacturing Applications Protocol, or MAP. MAP was the idea of General Motors of America, and ICL is one of the first companies in Europe to put it into practice. The idea is that different manufacturers can make their own islands of automation, but there are bridges of understanding to connect the islands. And what we most need, of course, is a map of the world. Not just to integrate manufacture, although many a multinational company would welcome that, but to integrate information systems throughout the manufacturing business. Beyond the factory, as information technology develops, we must develop a universal computer language. It must be a language which can communicate information, knowledge which every computer of every type can understand. And when the network of information technology is worldwide, as it will surely be in your lifetime, then it will be up to your generation, to you, to make sure that it generates activity and wealth. You must use it to the full in every activity you can think of. There will be those who in their ignorance will seek to dissuade you. It's all too much, they'll say. Just as the car has produced the traffic jam, so the computer will produce the information jam. There'll be a flood of information beneath which mankind will sink. Nonsense. It's not the car which produces the traffic jam, it's the motorist. And it won't be the computer which will produce a logjam of information. It will be those who use it carelessly. We can't have it both ways. We can't deny the computer wisdom, but ascribe to it folly. It is we who must make intelligent use of it, to the benefit of all mankind. Or rather, it is you who must get it right. We are beginning to show you how. At ICL, we are, I think, justly proud of CAFs. CAFs, Content Addressable File Store, a radical new approach to handling information. In an ordinary database, everything has to have its place. You must know where it is because you had to put it there to find it later. It has to be indexed. And the index can take up to half the available space. CAFs is index-free. You don't have to know where the information is before you can find it. Furthermore, it's a search system which asks many questions at once, not one at a time. The stream of data is passed through multiple electronic filters to extract the answers that meet all the requirements. For instance, by using CAFs, a professor of cosmology at Queen Mary College in London recently discovered that the universe is 10 times bigger than we thought. He was analysing the vast amount of data brought back by the satellite IRAS, which was in orbit for 10 months conducting an infrared survey of the sky. A survey which produced 600 megabytes, or the equivalent of 300,000 pages of assorted data. He could not have waded so quickly through all that without CAFs. He made that discovery before his international colleagues because he had CAFs. A database can contain not only plain facts, but opinions too, expert opinions. It can be well informed, a précis of the knowledge and experience of the expert, yet still readily accessible to the user, giving access not just to a host of facts, but to an accumulation of evidence, of probabilities, of considered opinions, of preferences. Knowledge engineering is the name now given to systems which provide the instant availability of the best advice. The advice of the doctor, the lawyer, the engineer, the experienced manager. But people will still have to have the nous to act upon it. The advice won't be the advice of the computer, but the advice of the expert made universally available through the computer. To act critically and practically on that advice is to exercise the human power of wisdom. But the power of today's computers is limited. Computers do things one at a time. At great speed, it's true, but nonetheless in sequence, or as we say, serially. And that produces enormous queues of information. What we need, and what we now have in the research laboratories, is the 5th generation of computers. With them, processing can be simultaneous, or as we say, in parallel. Not one process at a time, however quickly, but many processes at the same time. Not just to reduce the queues, the waiting, but as a means of getting closer to reality, because reality is infinitely complex. It cannot be reduced to a sequence of calculations. Let me give you a simple example. When two football teams meet, can you predict who's going to win? The simplest calculation is to count the players. They have 11 each. They're equal, it'll be a draw. Rubbish. All right then, we must look instead at form. Team B has won its last 3 games. Team A has drawn 2 and lost 1. It'll lose today. Ah, but Team B has never beaten Team A. Yes, they have, but not playing away. In any case, Team B is an unhappy team. The striker has stolen the sweeper's wife. True, but Team A's best defender hasn't recovered fully from the knee injury last week. And it may rain. The forecast said it would. But the forecaster was relying on the computer, and a computer has never won the pools. You see what I mean? Reality isn't one problem, but many, an infinite number. The 5th generation of computers will tackle many problems at once and address them in a different type of language. Alice, for instance, the applicative language idealized computing engine, now being built in Manchester by ICL and Imperial College London University. Alice is the entry to a wonderland in which computers will respond not simply to imperative language, do this, then that, then the other as normally programmed, but to declarative language. I want such and such, and you, the machine, work out how to get it. It's the difference between telling someone how to do something and simply asking for it to be done. Let me show you how a 5th generation system answers questions. Imagine a street in which there are 5 houses. 5 people live in those houses. Each has a different occupation, a different pet, a different favorite drink, and a different form of transport. But who has which? Well, this is what we know about them.
Mr. Black drinks tea. The coffee drinker has a dog. Mrs. Green lives at number 1. Mr. Brown is a plumber. A hamster is kept at the middle house. The person who drinks the soda is a teacher. Mr. White has a budgerigar. The Vauxhall is owned by Mr. Plum. Question 1. Whose car is the Jaguar? Question 2. Whose pet is the ferret?
To find the answers to those two simple questions from the data provided using fourth generation technology means writing a very complicated computer program like this, asking a whole series of questions in sequence. There are, in fact, over 24,000 million possibilities. Fifth generation technology doesn't progress serially step by step, but tells the computer what it knows and says you work it out. The program is simpler, and incidentally, the answers to the two questions are: the plumber owns the Jaguar, and the teacher owns the ferret. And although that was simply a frivolous game, its serious purpose was to demonstrate how much easier it is both to use and to understand fifth generation language. But as I said earlier, the fifth generation is not just about new languages, it's also about computer power. The new languages demand a significant increase in computer power, and the systems in use today, which are based on the von Neumann methodology of serial processing, have clear limitations in providing the power required. With the fifth generation, we're meeting the requirements for power by the development of parallel processing techniques. The ability, as I said, to process many problems simultaneously, indeed to act in a way similar to the human brain. Let me demonstrate the power of parallel processing using our research processor Alice. We'll use another CAD application.
The task is to design the physical placement and layout of components on a printed circuit board, a PCB. You start with a circuit diagram and design specification. In other words, you are told what is required and within what restraints. These include rules concerning the maximum length of tracking between components, the width of track, the gaps between tracks, the testing requirements, and so on. The task is to work out what we call the connectivity of the components, where they should go in theory. So first, we produce an abstract design, a theoretical design. Then, and this is the important bit, we produce a practical layout which will get all the components on the board in the positions which meet all the rules and specifications of the design and which optimize their interconnectivity. In this example, there are more than 200 components, which include microprocessors, integrated logic circuits, and resistors. To solve that problem today, using a fourth-generation computer, requires batch processing taking anything from 24 hours to several days. Use of the NMOS transputer, the computer on a chip. The computer is designed in a modular form, each module being a computer processor in its own right. If we use only one processor, the problem is solved in only 1 minute and 20 seconds. But we've been talking about parallel processing. If we add a further 7 modules to Alice and load the same program, the problem is solved in 10 seconds. So what could have taken several days is completed in several seconds.
That is parallel processing. That is computer power. The fifth generation will bring together a combination of improved languages and improved processing technology, a powerful combination. And if you still have your doubts, if you think that information technology is more trouble than it's worth, then think of this. At the very beginning of this lecture, we said that man was by no means the strongest or the swiftest creature on this planet. But it doesn't matter, because by his ingenuity, he can make up for all his handicaps. But what of those who are handicapped, who are a step behind the rest of us, who can't see or hear or move or lift, who can't speak or signal, who are cut off from mankind? Information technology can do wonders for them.
Tara is an albino. She has difficulty seeing, particularly in brightly lit surroundings. She also has an associated problem called nystagmus. This causes her eyes to make involuntary movements. But she and the screen are sensitive to her touch, and the teacher says she's learning by leaps and bounds.
You are strongly recommended to take advantage of our
Keith
fully
is totally blind, but his fingers are becoming word perfect, as his computer confirms when it reads back to him what he has written.
Cover, full stop.
INSURANCE space COVER. You are strongly recommended to take advantage of our fully comprehensive insurance cover.
Further along on that line, you've got another little mistake. See if you can find that one. Good, that's it.
That's it. So, you correct that paragraph and I'll show you to it. Good.
The denial of information technology is a handicap. That is what this lecture is all about. The denial of information technology is a handicap to a nation. 1986 was designated Industry Year in Britain. You may have wondered why. After all, every year is Industry Year in Britain and has been since 1786 or even earlier. The evidence is all around us. But so too is the evidence that Britain is not the industrial nation it once was. It's fallen behind the others, and I'm not surprised. When the men at Manchester University produced that first stored program computer in the world, the British government of the day could see nothing in it.
There will never be a need in Britain for more than 3 computers.
That was a cabinet spokesman. Since the Second World War, Britain has fallen from number 2 in the League of Prosperous Industrial Nations to number 14, and we're still on the way down. On present trends, we may soon be the poorest in Europe. And it's not only a reluctance to make changes that's held back Britain. It's a reluctance to acknowledge the importance of industry. Too many important people in this country say with false modesty, "Oh, this new technology is beyond me," meaning that they think it's beneath them. It's a silly attitude, and it's far too common. For the truth is that it's only by making the fullest use of the new technology that Britain can hope to prosper. The future is clear. The way in which things will be accomplished is already determined. The only question is, will Britain be in there? And it's not true that the new technology will put everybody out of work. It's already created more than 50 million jobs throughout the world, but not enough of them in this country. A Japanese trade union leader was asked by a BBC reporter how it was that Japan had adopted the new technology and yet had so little unemployment. It's very simple, he replied. We've imported your jobs. You'll understand now why we were so eager at ICL to stage this Faraday lecture. Not merely to entertain you, not just to tell you what we're up to, but to explain that what we do is what Britain must be doing if it's to survive and prosper as an industrial nation. That is the opportunity that beckons in your lifetime, and you must seize that opportunity. This is a most exciting industry to work in, and I hope that many of you will come to work in it. You don't have to be a physicist or a mathematician. You just have to be alive to the opportunities which information technology can create. You don't have to be a computer scientist to use it, any more than you have to be an automobile engineer to drive a car. You just have to know what it can do and want to do it. This is the electronic age, and you are its citizens. You want to get on in the world, I'm sure, and you want this country to prosper. This can only be achieved if we make better use than our competitors of the new technology. Yes, better use. In every walk of life, information technology is an enabling technology. The dynamo that Faraday invented brought electricity to the world and changed our lives. The computer is the dynamo of the electronic age, a technology to enable our brains to reach further heights of invention. How we employ this most powerful of man's creations is up to you. Every occupation can benefit from information technology. We need people of every discipline, professionals to work in information technology, to work on information technology, to work with information technology. Not just scientists and engineers, but everybody, whatever their interest or study, and I mean everybody, all of you. Those who employ its potential to the full will be enriched. Those who work on its development will be creating the most exciting machines ever. So join us for the 5th generation and lead us into the 6th and the 7th. The 6th, they say, will be high-speed optical computers with optoelectronic integrated circuits switching at the speed of light. The 7th may be closer to that most advanced information system of all, the human body. We call it bioengineering because it may use proteins to store knowledge, proteins which will be manipulated and made to breed by the use of organic material. Computers that grow. And many of you will live to see the 8th generation. I wonder if we can deduce what that will be. It sounds like a question for the computer. So the answer to that prediction lies in the future, and it lies with you. It's your future and your challenge. It's the opportunity of your lifetime. Thank you.
Good morning. My name is Sarah Mollard, and I represent the Institution of Electrical Engineers. It gives me great pleasure to thank our lecturer. He is the most recent in a long line of distinguished Faraday presenters, which goes back as far as 1924. This year's lecture has been rather different from its predecessors. The intention is to assist young people to obtain a better understanding of the use of information technology, for it is today's young people who will be most involved with the information revolution. All aspects of electrical engineering impact on society as a whole, but there is a general belief that it is the technology of computing, a field in which ICL is a leader, which is likely to have the most profound effect. Our lecturer has shown the subject to be exciting. Young men and women will have seen it as a most rewarding application for their talents, and I hope that many will be motivated to join the electrical engineering profession. We thank ICL as the sponsor of this year's lecture, and we are delighted that the Barbican has been host to this presentation. Ladies and gentlemen, please join me in expressing our warmest appreciation to John Gardner and all the people behind the scenes who have given us such an enjoyable, entertaining and thought-provoking presentation. Thank you.